Testing, can you hear me? Okay, I'm going public right now. So I'm going to be studying calculus again. I finished the discrete math book last stream. This stream I'm going to read about divergence theorem. That seems to be the last chapter in vector calculus, but like my knowledge in vector calculus is really weak. It's really difficult for me to understand. I do understand divergence and curl. Surface integral, I do understand it. I think the previous two streams was really difficult for me. After I read divergence theorem from this book, I'm thinking of opening some other book on specifically on vector calculus and reading it from there. Uh, so vector calculus, this is the last chapter remaining, and then there is only chapter 7. It seems to have 4 subchapters. Then I'll be done reading calculus 3, but I still need to practice. I'm planning to do more calculus stream in the future, like even after I finish this book. Okay, so on divergence theorem, let's read what this is and let's get an idea. I don't think I will understand this as well, but let's just try. So, overview of theorems. Before examining the divergence theorem, it is helpful to begin with an overview of the versions of the fundamental theorem calculus we have discussed. So we have the basic one, right? We have fundamental theorem for line integrals. Okay. Where P naught is the initial point of C and P1 is the terminal point. The fundamental theorem for line integral allows path C to be a path in a plane or in space, not just a line segment on the x-axis. If we think of the gradient as a derivative, then this theorem relates to the integral of the derivative over path C to a difference of f evaluated on the boundary of C. Green's theorem circulation form. Okay, we have this as curl f dot k. The curl is the derivative of sorts. Green's theorem relates the integral of the derivative of curl f of the derivative curl f over planar region D to an integral of f over the boundary of D. Green's theorem flux form by f dot n. Since this is wasn't this divergence? What was this diff over here? It was a divergence, right? Yeah, divergence of f. Divergence is a derivative of such. The flux form of Green's theorem relates the integral of the derivative of df over planar region D to an integral of f over the boundary of D. All right. Stokes' theorem, so curl f is equal to f dot dr. Isn't this the same as this? I think this is more general, right? Or this is for 2D, this is for 3D. The divergence theorem follows a general pattern of these other theorems. If we think of divergence as a derivative of sort, then the divergence theorem relates a triple integral of derivative t if f over a solid to a flux integral of f over the boundary of the solid. More specifically, the divergence theorem relates a flux integral of vector field f over a closed surface S to a triple integral of the divergence of f over a solid enclosed by S. Okay, I understood nothing. Okay, let's see. Divergence theorem. Let S be a piecewise smooth closed surface that encloses solid E in space. Assume that S is oriented outward and let F be a vector field with continuous partial derivatives on an open region containing E. Then the triple integral, the region E, divergence F dV is equal to the double integral S F dot ds. Okay, so Stokes' theorem talks about surfaces. Green's theorem talks about line. And I think divergence theorem, this over here, talks about the entire volume. Recall the flux form of the Green's theorem states that the double integral d divergence f dA is equal to the integral f dot nds. Therefore, the divergence theorem is a version of Green's theorem in one higher dimension. The proof of the divergence theorem is beyond the scope of this text. However, we look at an informal proof that gives a general feel for why the theorem is true. It does not prove the theorem with full rigor. Let B be a small box parallel to the coordinate planes inside E. At the center of P have coordinates x, y, z. Okay. Suppose the edge of the length is delta x, delta y, and delta z. The normal vector out of the top of the box is k. The normal vector out of the bottom of the box is minus k. The dot product f with k is r. Okay. The dot product with minus k is minus r. The area of the top of the box is delta s, which is delta x times delta y. The flux out of the top of the box can be approximated by r. X, y, z plus delta z over 2. Okay, r times this times it by delta x, delta y. So r times this. Flux out of the box is this. Delta x times delta y. And the flux out of the bottom of the box is minus r times, okay, minus r, the vector here times this, times it by the area. If we donate the difference between these values as delta, then the net flux in the vertical direction can be approximated by delta r, delta x, delta y. So this can be written as this, which can be written as this. Therefore, the net flux in the vertical direction can be approximated by partial derivative of r divided by partial derivative of z times delta v. So in the x direction we have this, and the y direction we have this, and the total flux is df f delta v. This approximation becomes arbitrarily close to the value of the total flux as the volume of the box shrinks to 0. Sum of df f delta v over all small boxes approximating E is approximately this. On the other hand, the sum of div f delta v over small boxes approximating E is the sum of the fluxes all over these boxes. Just as in the informal proof of Stokes' theorem, adding these fluxes all over the boxes results in a calculation of a lot of terms. If an approximating box shares a face with another approximating box, then the flux over one face is the negative of the flux over the shared face of the adjacent box. The two integrals cancel out. When adding up all of these fluxes, the only flux integral that survive are the integrals over the faces approximating the boundary of E. As the volumes of the approximating boxes shrink to zero, this approximation becomes arbitrarily close to the flux over X. Alright. The flux, the bottom of this cancels out with the flux on the top of the box below, right? The same goes for all of the boxes except for the ones that are on the edges. Verify the divergence theorem for vector field F and the surface S that consists of cone x square plus y square plus z square and the circular top of the cone. Assume the surface is oriented outwards. So what they're saying is cone is defined like this. Verify that the divergence theorem of the vector field and the surface S that consists of the cone x square plus y square equals z square. Circle the top of the cone. Assume this surface is oriented outwards. Div, dv, whoops. X minus y. X plus c. C minus y. Um, Wait, I forgot what divergence is. We write it as P U R, right? So P derivative P with respect to X, derivative Q with respect, okay. Derivative P with respect to X. No, divergence is It's a scalar value, right? So this would be 1 plus 0 plus 1, 2. Um, but the thing is, you have 2 and then volume of E, which is pi r square h over 3, which gives us 2 pi over 3. But isn't that, oh, they verifying the verify the divergence theorem? Okay. Pi r square over h, is that the formula? Pi r square h over 3. R is 1, right? Z, the max value of Z is 1. So the radius is 1. X, Y, Z. We have this gone, x plus y square equals Z square. When Z is 1, what is X and Y? Z being 1 is the height. That's also the radius. Isn't it just 2 over 3? Yeah. Now we want this f dot ds. F dot ds. Where is the formula for f dot ds? Is it this? No, I think it's below. It's the vector one. Why is it score up? Okay. It is this, right? S f dot ds. du x dy. Then dA. It's f of x y z x minus y. X plus c. And then we have the equation x squared plus y squared equals z squared. So then r u b instead of x I can write u. Instead of y I can write v. Is this correct? Or they use their own formula? Okay, so they did r u v as u. Okay, so they defined. Yeah, this is what we are supposed to do. This cone we are supposed to define it using r u v. They did it u cos v, u sin v1, and du dv. Then f of this. Oh, the x value. They replace the x value with u sin v. They replace this y value with u sin v. X value with u cos v. Then they got pi. Now we calculate flux over S2. A parameterization of this surface is S is piecewise smooth. S can be written as a union of smooth surfaces. Therefore, break the flux integral into two pieces. One flux integral across the circular top of the cone. One flux integral across the remaining portion of the cone. Oh, so this flux integral they're calculating, it's only for the lateral surface. Now they need a separate one for the top of the cone. Portion under the top is S2, call the circular portion circular top S1. So for S1, it's pi. For S2, it's minus pi over 3. Together, it's 2 pi over 3, right? Recall that the divergence of a continuous field F at a point P is a measure of the outflowingness of the field P. If F represents the velocity field of a fluid, then the divergence can be thought of as the rate per unit volume of the fluid flowing out less the rate per unit volume flowing in. The divergence theorem confirms this interpretation. To see this, let point let P be a point and let BR be a ball of small radius r centered at P. Let SR be a boundary sphere of BR. Since the radius is small and F is continuous, divergence of FQ is approximately equal to divergence of F at P for all other points Q in the ball. Therefore, the flux across SR can be approximated using the divergence theorem. Since F derivative at P is a constant, we have this. Therefore, flux can be approximated by divergence at P and the volume times at the volume of BR. This approximation gets better as the radius tends to 0 and therefore you have this. This equation says that the divergence at P is the net rate outward flux of the fluid per unit volume. The divergence theorem translates between flux integral of closed surface S and a triple integral over a solid enclosed by S. Therefore, the theorem allows us to compute the flux integral or triple integrals that would ordinarily be difficult to compute by translating the flux integral into a triple integral and vice versa. Calculate the surface integral where S is cylinder, including the circular top and bottom. Then F is equal to this. Example 6.78. S is a cylinder. So they want and S is described by x square plus y square equal 1 from 0 to 2. RUV x square plus y square equals 1. The radius is 1, right? So cos u sin u and v from 0 u 2 pi 0 v 1. Sorry, 2. And zero, 0, 1. Over 3 plus yc y cube over 3 minus sine xz. Z minus X minus Y. Um, the cross product of these two. Should I be using the applying the divergence theorem? Maybe this takes too long. I think I'm supposed to div F dv divergence of F. So we derivate the first one with respect to X. We get, so derivate this with respect to Y. Derivate this with respect to Z. We get 1. Now what? We want this over the volume, right? This times dv. Oh, it's adding. Whoops, adding. And then we have d dv. So we do it with respect to X, then with respect to Y, then with respect to Z, right? So X goes from uh, X square plus Y square equals 1. 0 to 1 for Z. 0 to 1 minus X square for Y. 0 to 2 pi for Y. Did they do something similar? 0 to 2, 0 to 1, 0 to 2 pi. Why did they do this? R square plus 1. dv is dz dr theta. What about this? R square plus 1. converting it to cylindrical coordinates. Why is there an R over here though? R square plus 1 times R dz dr d theta. So this dv is equal to f of this R dr d theta dz. Okay. Then they did R square plus 1 R dz dr d theta. Right. Um, let's see this last example. This time it's a cube. Let C be a solid cube given by this, and let S be a boundary of this cube. Find the flow rate of the fluid across S. The flow rate of the fluid across S is integral V dot ds. Before calculating this flux integral, let's discuss what the value of the integral should be. Based on figure 6.9, we see that if we place this cube in a fluid, the rate of the fluid entering the cube is the same as the rate of the fluid exiting the cube. Speed is rotational in nature, and for a given cube parallel to xy plane that has a center to the z-axis, the vectors along that circle are all the same magnitude. That is how we can see that the flow rate is the same entering and exiting the cube. The flow rate into the cube cancel out with the flow out of the cube. Therefore, the flow rate of the fluid across the cube should be 0. To verify this intuition, we need to calculate the flux integral. Calculating the flux integral directly requires breaking the flux integral into 6 separate flux integrals, one for each face of the cube. We also need to find tangent vectors, compute their cross product, and use equation 6.19. Further, using that divergence theorem makes this calculation go much more quickly. Divergence V, which is 0. There is no divergence C is 0. Therefore, the flux is 0 as expected. The divergence theorem has many applications in physics and engineering. It allows us to write many physical laws in both an integral form and a differential form. Areas of study such as fluid dynamics, electromagnetism, and quantum mechanics have equations that describe the conservation of mass, momentum, or energy. And the divergence theorem allows us to give these equations in both integral and differential forms. One of the most common applications of divergence theorem is to electrostatic fields. An important lesson in this subject is Gauss's law. This law states that if S is a closed surface and the electrostatic field E, then the flux of E across S is the total charge enclosed by S. We now use the divergence theorem to justify the special case of this law in which the electrostatic field is generated by a stationary point charge at the origin. If xyz is a point in space, then the distance from the point to the origin is r equal to root x square plus y square plus z square. Let Fi denote the radial vector field. Fr, the vector at a given position in space points in the direction of a unit radial field vector, this is scaled by the quantity 1 over r square. Therefore, the magnitude of a vector at a given point is inversely proportional to the square of the vector's distance from the origin. Suppose we have a stationary charge of q coulombs at the origin, existing in a vacuum. Charge generates electrostatic field given by this. In the approximation is an electric constant. The constant is a measure of resistance encountered when forming an electric field in a vacuum. Notice that E is a radial vector field similar to the vector gravitational field described in example 6.6. The difference is that this field points outward whereas the gravitational field points inward. Because E q over 4 pi. How do you pronounce this? Electric constant Fr is equal to this. We say that electrostatic fields obey an inverse square law. That is, the electrostatic force at a given point is inversely proportional to the square of the distance from the source of the charge. Given this vector field, we show that the flux across closed surface S is zero if the charge is outside of S, and that the flux is q over electric constant if the charge is inside of S. In other words, the flux across S is the charge inside the surface divided by the constant. This this is a special case of Gauss's law, and here we use the divergence theorem to justify this special case. To show that the flux across S is the charge inside the surface divided by the constant, we need two intermediate steps. First, we show that the divergence of Fr is zero. Then we show that the flux of Fr across any smooth surface S is either 0 or 4 pi. Can then justify the special case of Gauss's law. So R is this. The quotient rule gives us derivative with respect to x. We get this. And then derivative with respect to y, we get this. So what are they doing? Fr is defined by this. They multiply each component by 1 over r square, and then they are finding divergence. This, and this. We get 0. Notice that since the divergence of Fr is 0 and E is Fr scaled by a constant, the divergence of the electrostatic field E is also 0 except at the origin. Let S be a connected piecewise smooth closed surface and let Fr equal 1 over r square. Then we have this. 0 if F does not encompass the origin. 4 pi if F encompasses the origin. In other words, this theorem says that the flux of Fr across any piecewise smooth closed surface S only depends on whether the origin is inside of S. What does Gauss's law state? Suppose we have 4 stationary points. Wait. If I have, this entire thing is called Gauss's law, right? What is Gauss's law exactly? Gauss's law is this part, right? It's this part. Suppose we have four stationary points, point charges in space, all with charge 0.002 coulombs. The charges are located at 0, 1, 1, 1, 1, 4, minus 1, 0, 0, and negative 2, negative 2, 2. Let E denote the electrostatic field generated by these point charges. If S is the sphere of radius 2 oriented outward and centered at the origin, then find E dot ds. According to Gauss's law, the flux of E across S is the total charge inside of S divided by the electric constant. Since S has a radius 2, notice that only two of the charges are inside of S, the charge at 0, 1, 1 and the charge at minus 1, 0, 0. Therefore, the total charge encompassed by S is 0.004. By Gauss's law, we have 0.004 divided by this. By Gauss's law, where is it? I think it's this, right? Q is 0.004. Right. And then the exercises. Okay, I need a lot of practice in vector calculus because I think at the start, this chapter was going fine. And then quickly, I think after divergence and curl, these four chapters are is really not my thing. I need like an in-depth analysis of integral before talking about this. Okay, I will read this. Okay, next time I will start this chapter. Yeah. Then after I'm done with the calculus book, I will start like going looking for deeper books. Because I'm the reason I'm rushing through these ones is that because I want to study physics as well. I feel like in the electricity chapter they're going to be using uh, these equations. I just want to be familiar with them and then also want to get more in depth with them later on. Okay, I will end the stream here. And yeah, I will see you guys next time. Bye.